Yes, hello everyone and welcome to IFAS. I welcome you to the very new lecture series of organic chemistry, that is reaction mechanism. We have reached to lecture number 3. I will correct this. This is our lecture number 3 for this series. So don't be in panic. Where is lecture number 1, sir? Where is lecture number 2? This is lecture number 3. So, for you people, we have decided to teach this complete course, this complete series in medium English only. So, the students who face Hindi as a barrier for understanding chemistry, so I think that this will help them a lot. So, for now, we have reached till we have studied what is a substitution reaction. We have studied what are nucleophiles, how we can compare a nucleophile, what a solvent can do with a nucleophile. These all things we have covered. If you have been connected with me since the lecture number 1, then you must know what we are going to discuss today. So, welcome to the live lectures and good morning to each one of you who have joined. Good morning Ankita, good morning Pai, good morning Brajraj, good morning Praful, good morning Sadik, and welcome to the session. See, in the previous lecture we were discussing about a little bit. I have given you idea about the molecular orbital theory, how it works. Now, in today's lecture, as we have decided, as you have suggested, we should go in a deeper concepts of molecular orbital theory. So, I will give you a little flavor how molecular orbital theory can govern a substitution reaction. See, always there are two ways to study a reaction mechanism chapter. One is a very classical way, which we generally do, which is little on a easier side, and the second approach is of molecular orbital theory, that is MOT approach, that may be little tougher. Generally, books also don't prefer that approach, but we will take a little bit idea how molecular orbital theory works, so that if any question comes from the MOT approach, we are able to answer those questions. Okay. So good morning, Adi. Good morning, reagent boy. Good morning. What a unique name. So welcome to the live. If anyone is new to this lecture series, first of all, I want to give you a recap what we have studied. See, we have divided this whole reaction mechanism topic into few fragments in order to make it easier to understand and in order to make easy to retain into our minds what we study and how it will be easier for you to revise the lecture. Since we have three basic pillars: substitution, elimination, addition, and for CSIR and gate aspirants, few topics adds up. For example, Hammett equation adds up, which will take approximately 1 or 2 lecture, and we will finish the Hammett also. Substitution, we have started with the substitution. There are so much mechanisms which we need to discuss, but before that we are dealing with the basic part of the substitution reaction. For example, we dealt with what are the components of any substitution reaction. If you have attended the lecture, you must know the most important component was the nucleophile, right? How the nucleophilicity increases, decreases, what are the factors which may affect. We have done all these things. We have understood how a solvent can also affect the nucleophile. Moving ahead, we have seen the factors which can affect the nucleophilicity. These were like size, electronegativity, stability of an ion, and a hindrance. And of course, a solvent can also affect the nucleophilicity. Moving ahead, we saw that size, electronegativity factors were clear enough, stability was clear enough. In yesterday's lecture, I have discussed about the hindrance. As the hindrance goes on increasing for the anionic center, it is becoming larger and larger group. So it will be difficult for it to attack at the carbon center and to eliminate the leaving group. It will be easier for it to abstract a proton and perform an elimination reaction. So in such a situation, the anionic center is behaving as a base rather than a nucleophile. It means if we go on increasing the bulkiness of our anionic center, it is more likely to behave as a base as compared to a nucleophile. However, there is a very thin line. Anionic center can perform both as a base also, both as a nucleophile also. We will try to understand this, but it will be coming further in the lectures how we can differentiate whether the anion is going to behave as a base or substitute as a nucleophile. It will perform a substitution or elimination. Okay. So we will be covering this, but since we need to go through the basics first, after which we will see that topics. Now, the important one was effect of solvent. In the yesterday's lecture, we saw how solvent can also affect the rate of a nucleophilic substitution react, how it can affect the nucleophile. Then indirectly, it will also affect the rate of the reaction also. There are two types of solvents, a protic solvent and a aprotic solvent. Generally, a protic solvent decreases the nucleophilicity. Why? Because it performs solvation-like phenomenon which stabilizes the anion, and if anion is getting stabilized, then of course its nucleophilicity is going to be decreased. But still, the larger size anion is more nucleophilic in polar protic solvent, as we have discussed yesterday. In a polar aprotic solvent, we found that since the solvation sphere is very much disturbed because of the smaller size anion, hence the nucleophilicity increases for the smaller size anion. It increases for the larger size anion also, but the extent of increase is more in the case of smaller size anion. That's why for the first time we have seen that a small size F minus is a very having high nucleophilicity as compared to I minus. Got it? This was some important points which we have discussed. Now, living group, we know that if the anion is more stable, then of course the living group will be very good. I have given you an order which is for your living group ability. This may help you in some questions. Now, we were dealing with MOT approach. We have seen we have a substrate, we have a nucleophile. Substrates often involves its sigma star orbital, whereas a nucleophile always involves its non-bonding orbitals which contain non-bonding electrons. Correct? Now, we will go more deeper into this MOT in order to understand how this MOT works. Okay? So this was what we have discussed. Now I am going to start the today's lecture from the MOT part. Sir, how to study MH set for organic chemistry? In order to crack MS set, you need to go through the organic questions which have been asked in the previous year of set exam. That will be sufficient. If you are able to solve that questions, you are able to understand what are the concepts asked there, then you will be in a situation to solve the questions in the upcoming exam also. So Rahul, you need to solve as much questions as possible before the exam. This will be the major key to success, I think so. Okay. Okay. So now we want to see the MOT approach. See, I will be giving you a very simple example. Let's suppose I have a carbon chain and I have a fluorine at this center and a hydrogen at this center. Okay. And I have another carbon chain with a iodine at this center and a hydrogen at this center. Now we all know that the electronegativity for carbon, it is approximately 2.5, and electronegativity for hydrogen, it is approximately 2.1. This is what the data says when you see the periodic table. Okay. This is your 2.5, and for fluorine it is approximately, I can say, 4 or 4.5, because fluorine is the most electronegative element in the periodic table. So of course its electronegativity should be high. And I have put a nucleophile in front of them, a CS3 minus here also, and a CS3 minus nucleophile here also. Okay. Now what I see is the new electronegativity of carbon is 2.5, and for hydrogen it's 2.1. This carbon is also 2.5, and for this iodine is 2.4. Now in such a situation, what the classical theory says is, since fluorine is more electronegative, this will create delta negative at this center and delta positive at this center. Correct? In the second situation, when I am dealing with the iodine case, what I find is my delta positive is at this center. Sorry, the carbon being more electronegative will have delta negative at this center, and hydrogen will have delta positive at this center, because the electronegativity difference is more in the case of CH bond as compared to Ci bond. This is what the classical theory is saying, or this is what the electronegativity data is saying. It means if in the first case the delta positive and delta negative exist more in the case of CF, then my nucleophile should attack at this center, and in this case we will say that it is behaving as a nucleophile. I hope you are getting my concept, the concept which I am trying to convey. Since the difference of electronegativity is more in the case of CF, this should attack at the carbon center, so it will behave like a nucleophile. But in the second scenario, what is happening? The electronegativity difference is now more at the CH center. So the same CH3 minus should go at the H plus center and should eliminate it, and in such a situation it will behave like a base. This is what the electronegativity data says. Did you understand how I am saying that why in the first case it is going to behave as a nucleophile and the second case is going to behave as a base? Is this digestible to you or not? First of all, tell me this. Yes, Swati, Adesh, Chem Diary, Pooja, Mariam. Is this thing digestible? Since the electronegativity data is clear cut, it's creating a delta positive and delta negative. So at the center which is more delta positive center, the nucleophile should attack. So in the first case, the attack should be at the carbon center because the difference here is very high. And in the second situation, the attack should be at the hydrogen center because the difference in this situation is very high. But actually what we find that this does not behave as a nucleophile and it does not behave as a base. Oh my god, what is happening, sir? It should behave like this, but it is not behaving like this. It means here the VBT theory, or we can say the classical theory which we used to study, is failing. It is failed to explain what is happening here. In actual condition, the result was what? In the first situation, your anionic center was behaving as a base, and for the second situation, it was behaving as a nucleophile. But what is the correct scenario? Why this is happening so? So when VBT fails, when valence bond theory, or you can say the classical approach, is not able to explain such things, then comes your MOT, and now molecular orbital theory will explain you why this is happening here. Did you get the concept, or did you get the question from where we realize that yes, we need MOT to explain such things? Did you understand what is the contradiction in the above example? It's very important to understand first that yes, there is a contradiction happening here. How VBT is failing, now we need a theory which can explain these things also. Good morning, Kishore. Good morning. Yes, Pooja, did you get that? See, please try to respond in the comment section because I am only connected to you via this comments. So you need to write something, no? Okay. So I'm moving ahead, okay? See, so we need to understand how the MOT works and how MOT is going to explain these things. In order to explain this, first of all, let's draw a MOT diagram for any substrate. Okay, for any substrate, let's suppose we have a carbon and a halogen bond. For this sigma bond, yesterday also we have drawn a MOT which was like this. We have a sigma bond and we have a sigma star. The sigma is your bonding molecular orbital, this is your BMO, and this was your anti-bonding molecular orbital which was your sigma star. How this has been formed? You must have a carbon atom. Let's suppose this X group is our living group, that is Cl. Okay. So we have a carbon atom which belongs to second period. It lies here. Its atomic orbital we can say lies here. And for the case of halogen, since the electronegativity is little bit higher, you must have studied in chemical bonding that if electronegativity increases, its potential energy goes on decreasing. You must have seen that. So that's why the energy level of this halogen is somewhat lower as compared to the carbon center. I hope you are aware with this concept. So the carbon orbital exists here. When the overlapping take place, we form a bonding molecular orbital and a anti-bonding molecular orbital, which results into a sigma and a sigma star. This is how a substrate MOT is formed. The sigma bond which is involved in a reaction is formed. It has two electrons, so the sigma bond, that is sigma orbital, has two electrons. And this is your LUMO, that is your substrate in which it is going to accept the electrons. And now talking about the nucleophiles, let's suppose I have water as a nucleophile. Let's suppose I have I minus as a nucleophile, or let's suppose I have OH minus as a nucleophile. All these nucleophiles always donate their non-bonding electrons. Non-bonding electrons. And these non-bonding electrons are always present in their non-bonding orbitals, which are HOMO in nature, which are highest occupied molecular orbital, and they lie in the non-bonding energy level. I will not be drawing the MOT for water or OH minus. That is, you must have studied that in the your coordination, chemical bonding chapter also. But I will give you the brief idea how they are going to work. So what is happening from here? The nucleophile is donating its electron into the LUMO of the substrate. This is what the basic principle says. Now, what I am going to draw is a MOT for 4 different substrates into a single diagram, so that we can try to understand how the energy gaps between HOMO and LUMO can help us out to understand how the rate of substitution can be affected. Okay, so this was a basic thing which I have covered in the yesterday's lecture also. Now I am moving to draw a little more complicated diagram. Just don't try to copy fast. I will give you time. First try to understand how I am drawing the MOT diagram. Okay, no problem. Camp Pacific and Jai Shri Ram. I see. Let's suppose I have a carbon whose atomic orbitals lies somewhere here. It is a second period element. Now I am talking about some electronegative elements. That's why the potential energy is going to decrease little bit. So I will be having my iodine at this center, and iodine belongs to fifth period. So it is here. Now talking about iodine, and let's suppose I have bromine. Since bromine is more electronegative than iodine, so its potential energy is going to decrease more. Then we have chlorine, then we have fluorine. What I'm going to draw this MOT diagram for Ci bond, CCl bond, CF bond, and your CBr bond, and we will compare all of them. Now this is of fourth period, this is of third period, and fluorine is of second period. When the second period carbon and second period fluorine overlaps and form orbitals, one will be your bonding molecular orbital, which is your sigma, and one will be your anti-bonding molecular orbital, which is sigma star. The bonding molecular orbital for the CF bond is going to lie at the lowest energy level, because the extent of overlapping between a carbon which is of a second period and between a fluorine which is of a second period is going to be very fine. Very excellent overlapping will take place. So the bonding molecular orbital energy will be very low, as it is very much stabilized, and the anti-bonding orbital will be very high in energy because overlapping is very good. So the CF sigma exists here, so CF sigma star exists here. Now I want to ask you a simple question. If I want to draw, let's suppose for CCl, I want to draw sigma bonding molecular orbital for CCl. Should I draw it at the energy level upside of the CF or downside of the CF? What do you think so? I want to know whether you are getting the concept or not. I am trying to say if I will draw bonding molecular orbital for CCl bond, then it should lie above the CF sigma or it should lie below the CF sigma. This is what I am trying to ask. Very good, Utkarsh. Excellent. See, since chlorine belongs to a third period, the extent of overlapping is not going to be that good as compared to the fluorine. It means the energy level of bonding molecular orbital will lie somewhere here, sir, and this will belong to my CCl bond. Now, if I talk about CBr bond, then it's now very easy to tell, sir. It will be somewhere here. And if you draw for the Ci bond, it is going to be somewhere here. Understood? And these all molecular orbitals, are your bonding molecular orbitals. And they all are homo in nature because they all have 2 electrons filled in that. The sigma bonding is clear. Now, what if I want to draw a CCl bond, sigma star orbital, whether it should be below the CF sigma star or it should be above the sigma star? Some of you have given the answer also, sir, it should be below the sigma star because the extent of overlapping is not that good. So the gap between HOMO and LUMO, or I can say between the bonding and the anti-bonding, will be not that high. That's why if I draw the sigma star orbital, it will lie somewhere here. Carbon Cl bond, this is my sigma star for carbon Br bond, and this is my sigma star for carbon I bond. Are you able to understand how I have drawn all these 4 molecular orbitals into a single picture? And the molecular orbitals which are present here are called as anti-bonding molecular orbital, and they are of course LUMO of all the sigma bonds since they are vacant, but these all are filled with 2 electrons which are present in the carbon and the halogen sigma bond. Now, this is how the MOT of a substrate is going to look. Did you understood this or not? Good morning, Sakshi. Is this digestible to you? So I will be then I will be shifting towards the nucleophile. Do comment, is this digestible? No problem. Very good. Now let's shift to the nucleophile part. Okay. सर आप CUET के लिए क्लास क्यों नहीं लेते हैं? साक्षी जरूर लेंगे, अभी थोड़ा हम इधर एंगेज हैं तो उधर भी आएंगे तो क्लास लेंगे, पर आपकी क्लास चल रही है मेरे ख्याल से. चल. So now we have, let's suppose, a nucleophile. We are dealing in the halogen family. Okay, so we will be having halogens as a nucleophile as I minus. Let's suppose its homo energy level lies somewhere here. Now if I have, let's suppose, Br minus, since it is more electronegative than iodine, then of course the energy level of the HOMO will be little bit lower. I am not drawing the complete MOT for the nucleophile. I am just picking up their HOMO and representing them. Then we will be having Cl minus somewhere here. Then we will be having F minus somewhere here. This can be a set of nucleophiles for the halogen family. Similarly, we can also have a set of, let's suppose, in the oxygen family if we go, then S minus will be a nucleophile. Then OH minus will lie somewhere here because since the electronegativity increases, the potential energy of the HOMO also decreases. So its energy level is somewhere here. So oxygen will lie somewhere here. Now what is happening? These all are non-bonding orbitals which are filled with non-bonding electrons, and these are the electrons which a nucleophile donates into the sigma star orbital of the substrate. Now, what is the factor which is going to decide the rate of a substitution reaction? So what I identified is a rate of any substitution reaction. A rate of any substitution reaction was inversely proportional to, very important, it was inversely proportional to the gap between the HOMO and the LUMO. I repeat myself. The rate of substitution reaction is inversely proportional to the gap between HOMO and LUMO. Of course, the HOMO of nucleophiles and LUMO of the substrate. Now, what is happening? This nucleophile HOMO is donating its electron into the sigma star orbital of the substrate. If the gap between this HOMO and LUMO is very small, let's suppose they lie very close to each other, then it will be very easier for a nucleophile to attack into the sigma star orbital because the gap is very less. If I increase the gap very high, then it will be very difficult for a nucleophile to attack into the sigma star orbital. Are you able to get this concept? Why I am writing here the rate of nucleophilic substitution reaction is inversely proportional to the gap of HOMO of the nucleophiles and LUMO of the substrates. Is this clear or not? Please do reply in the comment section. I'm trying to give you a knowledge about how MOT can explain a substitution reaction. Yes, classical theory do works and we do not need MOT, but it's very important to know what is happening with the MOT theory and how MOT explains a substrate. Let's imagine if you sit into an interview for your PhD, then if you explain a reaction with the help of MOT, then the half task is done. The interviewer is flat enough and he will be of course impressed by you. So to have a knowledge of MOT is a very good thing. Okay. So now if the gap between the HOMO and LUMO is less, then of course the rate of substitution reaction will be high. Now according to this theory, if I compare the nucleophilicity between the among the halogen family, what I find is, let's suppose if I fix a substrate, that is we have a Ci as a substrate, and we need to compare the nucleophilicity. So for a nucleophile, the condition which is favorable is higher the energy of HOMO, more will be its nucleophilicity, because it will be easier for it to donate into the sigma star orbital. It means if according to the MOT theory, I write the order of nucleophilicity, or I can say if I choose a best nucleophile here among the halogen family, then what we find is best nucleophile. Can you suggest me which will be a best nucleophile for the halogen family? Tell me fast. According to the MOT theory, which will be a best nucleophile in the halogen family? Of course, sir, since I minus has its HOMO very high in energy, so it will be very easier for the I minus to attack. Hence, the I minus is going to be the best nucleophile. And this is what the classical theory also explained us. Classical theory explained with the help of size, but now we are dealing with the help of molecular orbital theory. These all energy orbital levels are HOMO, and nature of these HOMO are non-bonding molecular orbitals. If I talk about the nucleophilicity order, then higher the energy of HOMO, more easier will be it for to attack into the sigma star. So the order can also be written as I minus, Br minus, Cl minus, and F minus. Talking about oxygen family, the order can be written as SH minus, OH minus, and this is what we have dealt with the classical theory also. Are you able to get this concept? How we have written the nucleophilicity order as I minus, Br minus, Cl minus, F minus, and for the oxygen family as SH minus and OH minus. This was the same result we have obtained from the classical theory also. Now, use your brain. I am asking you a question. What if I ask you which substrate here is going to act as a best substrate? CCl, CF, CBr or CI? What do you think so? Tell me fast. Among these substrates, if I want to ask you which is going to act as a best substrate, then what will be your answer? Yes, spread fish. I am trying to connect how the classical theory or the size factor which you study is giving you also the same answer as the MOT is also giving you the same answer. Now, my question is, what do you think, which substrate here is going to be the best substrate? CCl, okay. Oh, you are writing I think so. If I am not wrong. Amit, Pooja, Chem Pacific, spread please. Aditi, CI, very good. See, if we see from the substrate side, sir, a substrate is good if its LUMO, that is lowest unoccupied molecular orbital, is lowest in energy. If it will be more lower in energy, it will be easier for it to accept the electrons from a nucleophile. So, applying the concept, if we write a best substrate here, then it is going to be your CI. It means if I write the whole order for the substrates, it is going to be your CI, then comes your CBr, then comes your CCl, and then comes your CF. And this is the same answer which we obtained from the classical theory also. Classical theory told us if I minus is eliminated, it's a very good living group. That's why the best substrate can be CI, and we have explained the same thing also with the help of molecular orbital theory. Did you get the concept? It means in order to do a substitution reaction, the LUMO should be low in energy for the substrate and HOMO should be high in energy for the nucleophile. If the gap between these two is very low, then the rate of substitution reaction will also be very high. Did you get this point or not? Now, we can draw the whole MOT for the nucleophiles also. For example, in in chemical bonding chapter, when you study molecular orbital concept, you draw MOT for water, you draw MOT for OH minus. So if you have your notes, go and have a look to the MOT. You will see that the non-bonding energy level, that is HOMO, will have the 2 electrons. I have just picked that HOMO and placed it here in order to make you explain. Okay. Yeah, see, Chem Pacific, the role of solvent varies. Okay, the role of solvent can also be explained on the basis of your MOT. Okay, the whole SN1 and SN2 can be explained with the help of MOT, but it becomes little bit complicated. And your question is, sir, in SN2, the aprotic solvent F minus X. So yes, we have not discussed yet the role of solvent, no? If solvent comes, then the role of solvent, yani, the MOT of solvent will also play an important role. We are just discussing the basic part, what we have discussed in the lecture number 1, how the size affects, so how I am relating the same with the MOT also. Okay, very good. So the question which we have seen, that the whole concept originated from a contradiction, which was this. Now, since VBT was unable to explain this reaction, why the CH3 minus is acting as a base here and why it is acting as a nucleophile here, will be very easily explained by your MOT theory. Now, I will be picking these 2 examples once again in order to explain this contradiction which happened just few seconds ago. We were having 2 scenarios, CH and CF bond. We have a CH3 minus here and we have a CH3 minus here. What happened was, in this situation it was acting as a base and in this situation it was acting as a nucleophile. But we didn't understand why this is happening because the electronegativity difference was saying something else. So when we draw the MOT diagram, I am just drawing the sigma stars, okay? So let's suppose CF sigma star exists at this energy level. So of course your CI sigma star will exist somewhere here because the gap will be lower, because CI bond, the extent of overlapping will be less. And since we have a similar nucleophile, so let's suppose its non-bonding energy level lies somewhere here. And of course, this is going to be your HOMO for the nucleophile, and this is going to be your LUMO for the substrate. Now, what we observed is, for the case of Ci, it is very easy for the nucleophile to attack into the Ci sigma star. It means the energy gap, or we can say that this delta E is very much approachable for the CH3 minus for the case of Ci. But for the case of CF, this gap is huge for this nucleophile. This, we can say that this delta E gap is huge enough for this CF for sigma star, so it is not able to donate its electron into the CF sigma star. Instead, it will be easier for this to attack into or donate its electron into CH sigma star orbital. That's why in the first case it is behaving as a base, and in the second scenario it was behaving as a nucleophile. Did you get the concept? Why in the first scenario it is behaving as a nucleophile and why here it is behaving as a base? Because the gap is too much high and it would prefer to attack into the CH sigma star orbital, whose energy must lie somewhere between CF and Ci. Got it or not? We can prove this reaction also, or we can prove this whole concept by an experiment also. The Claydon book gives you a experiment also, which proves that yes, the concept which we are dealing is right, or we can prove that we have a proof in a Claydon book that they says that yes, the I minus and the Ci substrate, they are best nucleophile as well as the best substrate also. What I am trying to say, when I will give you example, it will be very much clear. Okay, sir, how we can differentiate? What we want, you want to differentiate? I think you are trying to ask, sir, how we are going to know in exam that this is happening here and this is not happening here. Correct? See, it you will not be confused because there are few limited examples which examiner asks, and you very well know how to apply the classical theory. Okay, since I want to just give you how an idea how MOT works, so this is how the it is going to work. Your question part will be dealt with according to the classical theory only. Okay, you will not be facing any such problem there. See, if I have not told you any such concept and I have given you this question, you will be straightforward eliminating I minus, and in the first scenario you will be abstracting the proton because F minus will not be a living group. You will be doing on the basis of living group that I have told you in the previous lecture only. Correct? Camp Pacific got the concept. I am just trying to explain you how MOT works here, how MOT explains the same concepts. Hmm. Why it is, sir? According to Fazan rule, I am getting what you are applying according to Fazan rule. But sir, acid-base reactions are fast, reaction high. Why? So where I have not used acid-base reaction here. See, it depends upon how much acidic the proton is. No, so you cannot compare a substitution reaction and a acid-base reaction straightforward. Depends ki how much acidic the proton is. How it is an oxy acid, it is a carbon acid. It's lot depend on that also. Yes, that's the point, spread piece. I'm trying to say this, I'm trying to explain you this is how MOT works. No need to go into the deeper concepts. If you want to, if you are writing any, let's suppose, any mains answer sheet, or you are writing any exam, if you are writing UPSC mains or you are writing any college exam means your exam which is written in nature. So then you can explain these things. But for solving MCQ questions, for example, for NET, GATE and these type of exam, classical theory is enough to solve your question. Okay, that's why I ask you whether you want to know the MOT in detail or not, because it has not that much application for the question part which is asked in our exam. Okay, I explained, Amit. Told you it depends whether it is an oxy acid, it is an carbon acid. The acidity varies a lot between a carbon acid and an oxy acid also. The the thing which you are talking about, it is for the oxy acids which have very highly acidic protons. Okay. See, I will give you a proof also how these things can be validated. We were performing a simple reaction where we have CS3, CH2 and we have a CCl bond. Okay. Now, we were doing a reaction with the help of PPS3. The PPS3 is having a lone pair. This was attacking at the carbon center and the Cl group was eliminated, and we were forming our product, that is CH3, CH2 and a PPS3 here. PPS3 gets a positive charge and of course the substitution reaction has taken place. Now, in order to do this reaction, we were taking 3 days. This reaction was taking 3 days to complete. But when the same reaction was done with the help of I minus as a catalyst, we chosen our nucleophile was PPS3 and we add a catalyst, that is Ki, and a very little bit catalyst is added here. वो कहते हैं ना हिंदी में बस चुटकी भर हमने Ki डाल दिया. Okay, we have added a very little amount of Ki here along with the PPS3 and the results were shocking. We saw that this complete reaction was completed into 3 seconds. How this happens, sir? Because since I have introduced I minus, this is a best nucleophile. So of course, in the presence of PPS3, I minus will decide, yes, I will be acting as a nucleophile. It will attack on the Cl center and the Cl will be eliminated and the I will be present. Now, once this CI forms, this CI says that I am a best substrate also. My LUMO exists in very lower in energy. So, it becomes very easier for PPSC now to donate the electrons and abstract and to eliminate the I here, or we can say substitute the I here, and we get the complete product in just 3 seconds. So, this was the role of I minus here, and we get the product, and this product forms now in just 3 seconds. So this can be a question also in your exam. So this contains an important concept. I hope you got this concept, how a Ki catalyst helps this reaction to complete in just 3 seconds. Why? Because I minus is a very good nucleophile. It will attack, and this when Ci is formed, then it is a best substrate. It can accept the electrons from PPS3 because its LUMO is very lower in energy. So it can very easily accept the electrons and the product will be formed. So now we can complete this reaction in just 3 seconds. How many of you have got this concept? Why we are able to complete this reaction in just 3 seconds and the above one is taking in 3 days? Is this digestible to you or not? Tell me fast. Is this digestible to you or not? See, a simple question may arise in your mind, that is, sir, if we have CS3, CH2 and I, this is the best substrate, then why this is not happening that I minus is attacking again at this center and this is eliminating? Because I minus is a strong nucleophile. See, we have added the Ki in very small amount, just चुटकी भर डाला है ताकि वो I और consume हो जाए, so that when its I minus attacks on the substrate, it get finished. It does not remains in your solution. So it is No more here to attack at the carbon center. Once the substrate forms, I minus get consumed. Now PPS3 can very easily attack at this center and the I will be eliminated and the whole product just forms in 3 seconds. Yes, catalyst plays an important role here. What is a catalyst? When we use it in the starting of the reaction, we get it at the end of the reaction. It does not get consumed into the reaction. And similarly, here also we get our I minus back. So this is the behavior of a catalyst which we study generally in physical chemistry. Yes, the problem arises when we take I minus in excess. If we choose I minus in excess, then it will be very difficult for the PPS3 to attack at the CI center and to form this product. Got this concept or not? That's why we have just added very little amount of Ki. Do tell me in the comments, are you able to understand this concept? Understand this concept? See, this whole MOT is a very large picture. I can explain solvent effects also. I can explain SN1, SN2 all on the basis of MOT. But why to complicate ourselves? No, we are not going to write any mains exam or we are not going to write any theoretical paper. We have to solve MCQs at the end. No, so their approach should be a little bit different, but it is good to have a little bit idea. Whenever you sit in a, let's suppose, interview, if you can explain a concept on the basis of MOT, then please do that. It is very impressive. Yeah, the examiner will think or the interviewer will think, yes, he knows what is going behind the reaction. He knows the actual concept. Okay. So this is how things works for the MOT. Now I will not be going into much deeper of this. The what question can be asked from in our exam is a simple question: which orbitals are involved at the nucleophile side? You know very well. Which orbitals are involved from the substrate side? You know very well. That's it. What can be asked in our exam. The rest all we can answer on the basis of classical theory, what we have studied in our lecture number 1 and 2. Zunaid sir, Academy sir, quality is 144p only. Hmm? No, you can, I can increase the quality in your phone. Got this? So now once we have covered with the basic concept of substitution, now we have become eligible to study SN1, SN2 reactions. Got this? So I think I will be starting this SN1, SN2 in tomorrow's lecture only. For now, I am keeping this lecture this much only. It generally takes more time to explain MOT, but it's important to convey you the whole concept. I think you got the concept. That's it for the today's lecture. Yes, tomorrow's lecture we will be starting with the SN1 part, and I hope so. I will be covering SN1 and SN2 together into a single lecture, and we will also try to practice some questions also. Next week I have also planned the same lecture series where we will be practicing some questions also, so that once we have covered a basic portion of our syllabus, we should able to solve the questions also. Okay, the timings will be same. Tomorrow also I will be meeting you at 9 a.m. only. Do join sharp at 9 a.m. Daily, and the next week also I hope I will be meeting on the same time. Thank you so much. Take care. Bye bye. Let's meet tomorrow and happy learning.